So let's begin with section 1.1, Stern-Gerlach experiments. The originals were done in 1922. They rely on the fact that particles like electrons, protons, neutrons, and many others have intrinsic spin. Intrinsic spin behaves just like real angular momentum possessed by these particles when they're just standing still. And it's not clear where it comes from. It's a bit of a mystery, but one thing we can say is that there are arguments that demonstrate that it can't come from something actually spinning inside the particle. Particles have magnetic dipole moments also. And that means that they behave like tiny bar magnets. Now, it's not really due to this, but if the magnetic moment of a particle like an electron were due to something moving in a circular orbit, with charge Q, a point particle of mass m, so here's a little sketch. There's the particle of mass m moving in a circular orbit. It would make a little current loop. And the experts in E&M tell us that the magnetic dipole moment of this little current loop, mu, would be equal to the charge divided by 2 times the mass of the particle, speed of light, times the orbital angular momentum of that particle moving in its circular orbit. This speed of light is a feature of the formula using Gaussian units, not SI units. You should look in Appendix A for a comparison between the Gaussian formulas and the SI formulas in electricity and magnetism. In case you're not aware, the difference between Gaussian units and SI units is more than just the values of everything is different, but the whole equation has to change in most instances in E&M. And this book uses the Gaussian unit system, but it only appears occasionally, and it's not that bad if you're accustomed, like most of us, to the SI system. Anyway, this formula gives a relationship between a hypothetical magnetic dipole moment of a tiny orbit of a tiny point particle carrying charge and its orbital angular momentum, and we're going to use that formula to form analogous equation for the the relationship between the intrinsic spin, angular momentum, and the magnetic moment of a particle like an electron. By analogy, we write the magnetic dipole moment equals some dimensionless proportionality constant times q over 2mc times the spin angular momentum. Now, there's no question that the units are right in this equation because it's just like the formula we had from an orbiting point particle. And all of the things that we don't know about the origin of the spin and the origin of the magnetic moment of an electron can be hidden inside the proportionality constant g. This proportionality constant is obtained from experiment, and theorists try to predict what it should be. Experimental results support the hypothesis that the spin angular momentum and the magnetic dipole moment are correlated in their directions as the particle goes about its business. And that's what's built into the equation that we just wrote. Because this equation here is saying that the direction of the magnetic moment is the same as the direction of the intrinsic spin angular momentum, or possibly if g is negative or q is negative, they could be in opposite directions, but those are the only possibilities that this equation leaves us.